Welcome to Snacks Weekly on Data Science. This podcast is all about making data science and machine learning knowledge accessible and less intimidating. Today, we are going to talk about a data-driven framework for decision making. This episode is based on a tech blog titled Ladder of Evidence in Understanding Effectiveness of New Products, written by Meta Analytics team. Throughout this episode, we will break this topic down from both business and technical angles. Now, let's dive in. On the business side, let's take a look at the problem to be solved. Meta operates some of the largest consumer platforms in the world, including social apps used by billions of people such as Facebook, Instagram, WhatsApp. In this kind of environment, new features are constantly being launched, everything from small UI tweaks to entirely new product experiences. And the data science team behind them need to answer one critical question every time. Is this product actually working, or will it work? But that's harder than it sounds. The challenge is that not every product can be tested in the same way. Some experiments are too expensive to run. Some have sample sizes that are too small to be reliable. And sometimes, a product gets launched to everyone at once, leaving no control group for comparison. So that's where the analytics team introduced a structured thinking framework called the Ladder of Evidence. The goal here is to help data scientists make smarter, more confident, and more defendable decisions to guide product direction. Now that we've understood the business context, let's dive into the technical side to see what this framework actually looks like. Let's start with the gold standard. The foundation of this framework is the randomized control trials, or RCT, which is for most of us known as A/B test. It involves randomly assignments of the control and test, and that random assignment eliminates bias, which is why RCTs are considered the gold standard for establishing causality. If the treatment group outperforms the control group, you can confidently say that the product caused that improvement. But here's the tricky part. RCTs aren't always possible. The team identified 4 common scenarios that the data scientists regularly encounter, and this is where the framework really becomes useful. In the first scenario, everything works perfectly. You can run an RCT with a large enough sample size and a manageable cost. In this case, the answer is simple. Just run the RCT and use it as your primary evidence. No debate needed. In the second scenario, you can run an experiment, but your sample size is small. This happens a lot in early-stage product development. For example, if you've launched a new feature to a limited group of advertisers, you might only have a small amount of data. In this case, the experiment is underpowered, meaning even if the product is working, the test might not detect it. So the blog recommends supplementing the RCT with causal inference methods to increase confidence and improve generalization. In the third scenario, running an experiment is technically possible but very expensive. Maybe you're competing with other teams for the same user population, or the infrastructure required to run a test is limited. In this situation, causal inference methods can serve as a cost-efficient way to get early direction insights, essentially giving you a preview of whether the product is likely to work before committing to a full-scale experiment. And in the fourth scenario, experiments simply aren't feasible at all. Sometimes the product must be launched to all users at once, with no control group. In that case, causal inference becomes your only option for evaluating effectiveness after launch. But it's also important to interpret these results carefully and wherever possible, compare them with evidence from past experiments. Among the above 4 scenarios, we have seen that causal inference is a very good complement of the standard A/B testing. So what is causal inference exactly? Causal inference is a set of statistical techniques used to estimate cause and effect relationships without random assignments. Instead of splitting users randomly, you use statistical measures to account for pre-existing differences between groups. It's similar to how medical studies adjust for factors like age or health conditions when randomized trials are possible. These measures are more complex and rely on stronger assumptions than standard A/B testing, but they are incredibly valuable when experiments are an option. Now, to make this more concrete, this blog walks through a real example, Meta's omnichannel ads product, which helps advertisers drive both online and in-store purchases. For this specific example, in the early prototyping stage, there wasn't enough adoption to run a meaningful experiment. So the data science team used causal inference method to build an initial understanding of the product effectiveness, looking at how advertisers interacted with similar tools. This provided a direction signal, which is very useful for guiding early strategies. As the product moved into alpha and the beta stage of testing, small-scale experiments became possible. Those weren't large, definitive A/B testing results, but they helped the team gradually build confidence about the product direction. Then, as the product scaled toward full launch, large-scale A/B testing became feasible. At this stage, the stakes were much higher, so the team ran multiple rounds of high-confidence experiments before making final decision. Throughout this process, causal inference was also used to prioritize features for a minimum viable product. There wasn't enough capacity to test everything with A/B testing, so lower confidence measures helped identify the most promising ideas to explore further. This is how the case study of Meta looks like within using this framework. What I really like about this blog is that it doesn't just explain a methodology, but provides a practical decision framework to use. First, you need to understand the constraints. Can you run an experiment? Can you have enough sample size? What are the costs associated with that? Second, align with your cross-function partners on what decisions this analysis will influence. The bigger the decision, the stronger the evidence one needs. The third one is choose the right methodology based on those constraints and the level of impact. Finally, be transparent about the level of confidence. If you are using causal inference instead of an A/B testing, make that clear and explain what it means for how the result should be interpreted. This last point is especially important. There is a big difference between saying this product causes better performance and saying this product is associated with better performance. One implies strong causal certainty, while the other acknowledges uncertainty. And for teams making real business decisions, that distinction matters a lot. Now we've discussed both the business problem and the technical solution. Let's wrap it up. In this episode, we explored how Meta uses ladder of evidence framework to evaluate the effectiveness of new product features. Instead of relying on a single method, this framework helps teams choose the right type of evidence based on real-world constraints, leading to better and more informed product decisions. If you like the content of this episode, please subscribe to the channel. Give me a 5-star review and leave a comment. Your feedback is very appreciated, and I'll see you next week.